The last concepts I want to talk about in terms of applications of DFS are the notions of acyclicity and topological sort. Okay, so I remind you that a cycle in a graph. Okay, so if you give me a directed graph, G, a cycle is basically a set of nodes U1, U2, U3, UK, U1. Okay, so we have such that we have an edge from U1 to U2, U2 to U3, U3 to U4, all the way to UK to U1. So it ends up being, okay, so we end up having in the graph the following structure. So if this is U1, U2, and UK, we have a cycle here. Okay, now a graph is acyclic if it doesn't have a cycle. Okay, so we have one important class of the directed graph is the notion of directed acyclic graph. Directed acyclic graph, or DAG. Okay, directed acyclic graph is a directed graph that has no cycles in it. Okay, and this is a very, very important structure if you think about directed acyclic graph. So if I want to, for example, give an example of a directed acyclic graph, I can draw something like this: A, B, C, D, E, C to E, and let's say F here, something like that. So this is a directed acyclic graph. If you look at it, it is directed, there is no cycle in it. Okay, directed acyclic graphs are very, very important in many applications. One of them is that if you look at this directed acyclic graph, it's basically describing a partial order. Okay, so partial order, what does this mean? It means A comes before B. If you look at this graph, it tells me A comes before B, A comes before C. In fact, A comes before all these nodes. B comes before D, before E, before F. B does not come before C. C does not come before B. Okay, so B and C here are not comparable under this graph. I cannot tell B came before C or C came before B. Now, partial orders are very important. So if we want to represent subsets, for example, the relationship among subsets of a graph, then we have a partial order that's represented as a directed acyclic graph. We use DAGs in evolutionary biology a lot because you represent evolutionary histories that involve processes such as horizontal gene transfer in bacteria and so on. One very important use that we can actually use it all the time in the university setting, which is the prerequisites. So if we want to capture the prerequisites of all courses at RISE, we have a node for every course, and we have an edge from course A to course B if A is a prerequisite to B. Okay. Now notice, for example, 182 can be a prerequisite to 215, 182 can be a prerequisite to 382, and 382 might not be a prerequisite to 215, and 215 might not be a prerequisite to 382. So the directed graph that captures the prerequisites of courses is a directed acyclic graph. It makes no sense to have a cycle in such a graph. I cannot say you have to take 182 before 382, and you have to take 382 before 481, and you have to take 481 before 182. Then we will have a deadlock and students will never graduate. So DAGs are used in this. There's a very important probabilistic graphical model in probability theory known as Bayesian networks. Bayesian networks have big uses in many applications. The graph underlying Bayesian networks is also a DAG. Another application of DAGs is if you look at the connections or the dependencies among variables in a computer program. Okay, so you can, for example, you evaluate the variable x. X is used then by in two lines, one that's adding x to something and one is multiplying x by another thing. The structure that captures these kind of dependencies is also a DAG structure. Okay, So DAGs are very important. Testing whether a graph is acyclic or not is very important as well. So the first task that we have is, given a graph, given a directed graph G, is G acyclic? Well, we want to check if there is a cycle, and if you understood the notion of DFS and the classification of edges, you should immediately have a simple algorithm for finding if a graph has a cycle. Remember that when DFS is working, it visits from A to B, B to C, and as it's exploring an edge, it might find sometimes what we call the back edge. Well, it turns out that if the graph has a cycle, then DFS will find a back edge. And if DFS finds a back edge, the graph has a cycle, okay? In other words, the graph is cyclic if and only if the graph has at least one back edge. So the algorithm for testing whether a graph is acyclic or not is very simple. Run DFS, and as you run DFS, if you find a back edge in the graph, you just return that the graph has a cycle in it. Okay, so it's very, very simple test. So it's a linear time algorithm that finds if the graph has a cycle. The second task that we want to do is what we call topological sort. Topological sort is, I want to print the nodes of a DAG, print the nodes of a DAG such that if U reaches V, there's a path from U to V, U must be printed before V. Okay? If there is no path from U to V or V to U, we are not saying anything. Okay, so topological sort, print the nodes of the graph in such an order. So if I go back to this graph here on top, and I want to do topological sort, A has to come before B and C, B has to come before D, so I can print A before B, B has to be before D, D has to be before E, E and F have nothing to do with each other, but D has to be before F, right? And A has to be before C. And C has to be before E. So can I put this here? The answer is no, this will not work, because under this order, E came before C, but in the graph, C must come before E. So if I want to print this, I have to put A. One topological sort is, let me print B and C immediately after A. Then I can print D, and then I can print E and F. Now, if you look at this order, there is a path from A to every other node in the graph. A is coming before all of them, okay? There is a path from B to D, E, and F. B is printed before D, E, and F. There's a path from C to E only. C is coming before E in the order. There's a path from D to E and F. D is printed before E and F. E and F at the end, they don't come before anything, so this is fine. So this is what we mean by topological sort. Why do we care about topological sort? Again, think back about the notion of courses and prerequisites. Topological sort basically gives possible plans for the students in which to take the courses. So if this DAG on top here is the DAG of prereqs, this order A, B, C, D, E, F is an order in which the students can take these courses, okay? And the students cannot take A, then D, then B. This is impossible. So topological sort gives us an order in which to execute tasks that are corresponding to these nodes, okay? The task can be, again, taking the course, or imagine that this is a DAG that is doing some, so we have concurrent programming, and each one of these nodes correspond to a function. The edges capture the dependencies among these functions. Then the topological sort gives us one sequential order of execution of these tasks. Okay, so if I want to execute the task sequentially, I can execute A, B, C, D, E, F, and I will be in good shape here because I could not, for example, execute D before B, because D depends on the values or the output of B. So if you think about this, again, this is another case where DFS readily gives us an algorithm for topological sort. So if we want to do topological sort of graph G, is we need to do DFS on G. And remember that DFS is going to compute again the discovery time and the finish time. And we can basically now, we compute the finish time for all the nodes in the graph, and we can now print them, print the nodes of G in decreasing order of their finish time. Okay, because remember, if there is a path from A to B to C, and I started the visiting from A is going to be finished last. Okay, so the finish time of A is going to be the highest. Again, so if I go back to this graph here, I start with A, I discover A first, then I discover B, then I discover D, then I discover E, for example, then I discover F, then I'm done with F, I am done with E, this is 7, I'm done with D now, this is 8, I go back to E, I'm done with B, this is 9, I come back to A, I'm not done with A because it has neighbor C, so C now is detected or discovered at time 10, finished at time 11, I come back to A, which is at time 12. So if you look at A, which is the one that should be printed before everything else, its finish time was the highest. So I can go now by decreasing order of finish time. 12, I can print A, then 11, I can print C, then I go to 9, which is B, then 8, which is D, then I go to 7, which is E, and 6, which is F. And this is another topological sort order that will work for this DAG. Okay, so we can just do DFS on the DAG. Again, the assumption is the input graph has to be DAG. If it has a cycle, we are going to run in problem here. So it has a DAG, and we just compute DFS. We print the nodes in reverse order or in decreasing order of their finish time. Of course, printing them in their finish time, you can also insert them into a linked list or into an array that based on these and print them. Okay, so to do topological sort, compute DFS, print the nodes in decreasing order of finish time. Running time is O of M because the time is dominated by the time of running DFS.